For more than 3 centuries, Newton's second law, force equals mass times acceleration, has stood as the bedrock of our understanding of the physical world. It's a simple equation, F equals sine ma, but its implications have rippled through every corner of science, shaping the way we see the universe and our place within it. This single equation unlocked the secrets of motion, allowing us to build bridges that span rivers, launch rockets that escape Earth's gravity, and predict the elegant dance of planets across the night sky. It's the silent architect behind our greatest engineering feats and our boldest explorations. Newton's laws gave us a sense of order, a universe that seemed not just understandable but almost clockwork in its predictability. For generations, scientists believed that with enough information, we could foresee the future of any object, from a falling apple to a distant star. But what if this foundation isn't the whole story? What if force, mass, and acceleration are just the surface, mere shadows cast by something deeper and stranger? Today, physicists are beginning to suspect that the universe is far more mysterious than Newton ever imagined. Imagine Newton's laws as the blueprint for the first few floors of a skyscraper, solid and reliable for what we can see and touch, but limited when we try to reach higher, to the very edges of reality. As we build higher, venturing into the realms of the very fast, the very massive, or the very small, the rules begin to shift. The familiar physics we once trusted starts to warp, revealing cracks in our old certainties. To question F equals sine ma is to question the ground beneath our feet. It's a challenge that shakes the foundations of what we thought we knew, forcing us to reconsider the very nature of reality itself. This isn't just an academic exercise or a puzzle for physicists, it's a profound re-evaluation of our place in the cosmos, a journey that invites all of us to wonder, what if the universe is stranger, more beautiful, and more surprising than we ever dared to dream? We stand at the edge of a new understanding, one that asks us to let go of old certainties and embrace the unknown. The next breakthrough may be just over the horizon, waiting for us to open our minds. So let's look at the universe with fresh eyes, curious, open, and ready to be astonished by what we find. To appreciate the revolution, we must revisit Newton's vision in the 17th century. Before Newton, the world was chaotic. Apples and planets seemed governed by different rules. Newton united them with his laws, especially F equals sine ma, revealing a universe governed by universal principles. This equation linked force, mass, and acceleration in a way that let us predict motion with precision. Suddenly, the universe became a grand, intricate clock, predictable and knowable. If you knew the forces and masses, you could calculate the future. This deterministic worldview gave humanity a sense of control and understanding. F equals sine ma became the master key to the cosmos. But was it the whole story? Newtonian physics became the default lens for understanding reality. In classrooms, F equals sine ma was taught as an absolute law, not just a model. We used it to solve problems from pushing boxes to launching rockets, reinforcing its universal status. This success led us to see the world as a giant billiard table, every motion a result of a prior force. Newtonian mechanics powered the Industrial Revolution and the space race. For our everyday world, F equals sine ma seemed flawless, but we mistook its success for ultimate truth. We became carpenters who saw every problem as a nail, missing the screws and bolts. The equation worked for the middle ground, but faltered at the extremes. We didn't realize our trusted tool would fail in new realms. For centuries, Newton's laws seemed unbreakable, pillars of certainty that shaped our understanding of the universe. They explained everything from falling apples to the orbits of planets, and for generations, no one could imagine a world where Newton's rules didn't apply. But as science advanced, we began to probe the universe's most extreme frontiers, places and conditions Newton could never have dreamed of. At speeds approaching that of light, Newton's famous equation, F equals sine ma, predicted that objects could accelerate endlessly, gaining speed without limit. But when scientists built powerful machines to test these ideas, like particle accelerators, they discovered a fundamental barrier. Nothing could surpass the speed of light. No matter how much force was applied, particles stubbornly refused to break this cosmic speed limit. Instead, as particles were pushed faster and faster, they became harder to accelerate, as if their mass was mysteriously increasing. The closer they got to light speed, the more energy it took, until it became impossible to go any faster. Newton's laws simply couldn't account for this strange new behavior. Even in our own solar system, Newton's law showed cracks. Mercury's orbit, for example, displayed a tiny but persistent wobble that defied Newton's predictions. Astronomers puzzled over this anomaly for decades, searching for hidden planets or unseen forces, but the answer lay beyond Newton's reach. The cracks widened even further at the quantum scale, where the rules of Newtonian physics seemed to dissolve entirely. Here, particles don't have definite positions or velocities. Instead, they exist in a haze of possibilities, behaving in ways that defy common sense. In the quantum world, certainty gives way to probabilities. The very act of observing a particle can change its state, making the universe far less predictable than Newton ever imagined. The idea that a force always produces a predictable acceleration no longer applies. At these scales, the universe plays by rules that are fundamentally different from those Newton described. Newton's map of reality worked beautifully for the familiar world of apples and planets, but it broke down in the realms of the very fast, the incredibly massive, and the unimaginably small. The universe turned out to be far stranger and more mysterious than the clockwork cosmos Newton envisioned. The rules, the language, and even the very nature of reality itself became profoundly weird, challenging everything we thought we knew. Newton's laws were just the beginning, a crucial first step on a journey that would lead us to deeper, more mind-bending truths about our universe. Enter Einstein, who didn't just patch Newton's theory, he rebuilt it from the ground up, daring to question the very fabric of reality itself. At the dawn of the 20th century, the world of physics was about to be turned upside down. Special relativity revealed a universe where the speed of light is not just fast, it's the ultimate speed limit, unbreakable and absolute. No matter how quickly you move, light always races past at the same speed. This astonishing idea forced us to see space and time not as separate entities, but as threads woven together into a single four-dimensional tapestry, space-time. As objects approach the speed of light, time itself stretches and slows for them, while their mass swells. This isn't just theory, particle accelerators and cosmic rays prove it. To push anything with mass past light speed would require infinite energy, a feat nature simply forbids. Newton's famous F equals sign may, so reliable for everyday speeds, turned out to be only an approximation, a shadow of a deeper reality that emerges at high velocities. Then, with general relativity, Einstein shattered the old view of gravity. Gravity wasn't a mysterious force acting at a distance, but the result of mass and energy curving the very geometry of space-time itself. Imagine a heavy ball on a trampoline. It bends the surface and smaller balls roll toward it, not because they're pulled, but because they follow the curves. In the same way, planets and stars move along the bends and dips in space-time created by mass. This new vision explained mysteries like Mercury's odd orbit, which Newton's laws couldn't quite predict. Suddenly the idea of force was revealed as an illusion. Objects simply follow the natural curves of space-time. Newton's laws described the shadow, not the substance, the visible effects, but not the hidden machinery beneath. In Einstein's universe, space-time itself became dynamic and alive, warping, stretching, and rippling in response to mass and energy. It was no longer a passive stage, but an active player in the cosmic drama. The familiar F equals sign ma faded in the face of these deeper truths, replaced by equations that described a universe far stranger and more beautiful than anyone had imagined. The cosmos, it turned out, was more flexible, interconnected, and mysterious than Newton ever dreamed, a place where the rules themselves could bend, and reality was richer than our wildest expectations. If relativity reshaped the very large, quantum mechanics shattered our intuition about the very small. In the quantum world, F equals sign ma loses meaning. Particles exist as clouds of probability, not definite objects. The Heisenberg uncertainty principle says you can't know both position and momentum exactly. This isn't a flaw in measurement, it's a feature of reality. Particles like electrons don't have single locations until measured, they're waves of probability. Energy is exchanged in discrete packets or quanta, not smoothly. Electrons jump between energy levels instantly, not gradually. Forces become exchanges of particles, like photons for electromagnetism, rather than continuous pushes or pulls. The classical idea of force is replaced by a chaotic, probabilistic dance. F equals sign ma is an illusion that emerges only at large scales. The quantum world is fundamentally weird. Relativity and quantum mechanics force us to ask, are force, mass, and acceleration truly fundamental? Modern physics suggests they're emergent properties, not basic building blocks. In general relativity, gravity is geometry, not force. In quantum field theory, forces are particle exchanges. Mass isn't intrinsic. It arises from interactions with the Higgs field. Even acceleration becomes complex in curved spacetime, described by tensors, not simple vectors. The elegance of F equals sine ma gives way to a richer, more intricate reality. The universe is more than pushes and pulls. It's a dynamic interplay of fields, geometry, and information. This isn't just philosophy. Understanding force, mass, and acceleration matters for technology and exploration. GPS satellites rely on Einstein's relativity. Without it, your phone's location would be off by kilometers daily. Our technology works because we account for the deeper physics beyond Newton. To study black holes or the Big Bang, Newton's laws are useless. We need quantum gravity, a theory still in progress. Even the mysteries of dark matter and dark energy require us to move beyond classical ideas. Our quest for understanding shapes the tools we build and the questions we ask. The universe demands more than Newton's equations. Embracing new physics is essential for progress. The future depends on seeing beyond the familiar. We've journeyed from Newton's apple to quantum fields and curved spacetime. F equals sine ma wasn't proven wrong. It was outgrown, as science refined its models. Each new theory explains why the old one worked and where it fails. Scientific progress is not demolition, but refinement. Each layer builds on the last. We underappreciated Newton's context, mistaking a chapter for the whole book. The universe is not a simple machine, but a web of energy, information, and geometry. Our understanding is still evolving, and that's the most exciting part. Science is a process of questioning, not memorizing facts. The greatest discoveries come from asking, is this the whole story? The universe is waiting for our next question.